So hello everyone and welcome back to the science class. I've been told my slides are quite boring, so I added my bit emoji there. So today what we're going to be talking about is we're going to talk about Regents practice problems for gas laws. So everyone knows in New York State and abroad there's some sort of standardized state exam. So these are all previous New York State Regents exam questions. So we're going to be learning how to dismantle these by reading the prompts, looking at all the figures, tables, graphs, whatnot, and solving these multi-step problems. Okay, so first things first, let's just remind ourselves of the gas laws. So I'm not going to write out all three of the gas laws. I'm going to show you P1, V1 over T1 equals P2, V2 over T2. Now, one other thing is we're going to see in the problems it mentions something called STP. STP just stands for standard temperature and pressure. So what is standard temperature and pressure? Well, we can find this on table A of our reference tables. And we know that standard pressure is equal to 1 atmosphere, or in other units, 101.3 kilopascals. Temperature, on the other hand, is 273 degrees Kelvin, which is also equal to 0 degrees Celsius. Don't forget, though, when we're using gas laws, when we're solving gas law problems, we need to indicate our temperature in units of Kelvin. For pressure in the combined gas law, it doesn't matter if we're using atmospheres or kilopascals, but we do have to keep it constant. Okay, so let's look at this problem. So of course, when we're solving a Regents problem, we need to read the prompt fully. One of the skills that you need for the Regents is being able to dismantle the prompt, figure out what is applicable, what's not applicable. So here's the prompt. A rigid cylinder is fitted with a movable piston, so we know the volume can either increase or decrease because the piston is movable. The cylinder contains a sample of helium gas. Now, we haven't seen any factors in which the type of gas matters, so we don't have to pay attention to the fact that it's helium. Now, this helium has initial volume of 125.0 milliliters. We also see this from the graphic. And initial pressure of 1 atmosphere. We can also see this in the graphic. The temperature of the helium gas sample is 20 degrees Celsius. Okay, so let's read our actual question. Helium gas is removed from the cylinder, and a sample of nitrogen gas is added to the cylinder. The nitrogen gas has a volume of 125 milliliters, pressure of 1 atmosphere, temperature of 20 degrees Celsius. Compare the number of particles in this nitrogen gas sample to the number of particles in the original helium gas sample. Okay, so number one, there's no calculations needed for this. Now, if we look, the helium gas sample also has a volume of 125 milliliters, also has a pressure of 1 atmosphere, also has a temperature of 20 degrees Celsius. The factors are exactly the same between these two gases. Now, you may or may not remember Avogadro's law. We've heard of Avogadro when we look at Avogadro's number for calculating moles, molar masses, and things of that nature. However, Avogadro talked about gases as well. So if the factors remain constant, especially volume, within a sealed container, as long as all the factors are the same, or volume, then it's the same number of particles despite what type of gas is in there. So for example, we have helium gas, and then we empty it and put nitrogen gas. All the factors are exactly the same. So that means there's an equal number of particles. And this is due to Avogadro's law. If we look at a different problem, draw an Erlenmeyer flask, and this is sealed. Then we draw another Erlenmeyer flask, and this is sealed. And this is 10 mLs, let's say. And this is 10 mLs. Well, they're going to have equal number of particles, even if this is helium. And this might be something like carbon dioxide. Yeah, we know carbon dioxide is significantly larger than helium atoms because there's 3 atoms in carbon dioxide. But according to Avogadro, it doesn't matter how big the particle is. as long as the volume is the same and we didn't mess with the temperature or pressure, things of that nature, equal number of particles. All right, let's move forward. So these questions are going to have the same exact prompt. So the piston is pushed further into the cylinder, so I'm decreasing the volume. In the space below, show a correct numerical setup for calculating the volume of the helium gas that is anticipated when reading on the pressure gauge is 1.5 atmospheres. The temperature of the helium gas remains constant. So this is a Regents question. We know we're going to use the combined gas law. So P1 V1 equals P2 V2 over T2. Now this says show a correct numerical setup. So we don't have to actually follow through with the math and solve algebraically for the new volume. We just have to set it up. Okay, so the initial pressure, initial volume, second pressure, second volume, temperature remains constant. So because temperature remains constant, let's cross off the temperatures. Now I get the formula P1 V1 equals P2 V2. All right, so we know we originally had 1 atmosphere. If we go back 1 atmosphere, original volume is 125. So 125 equals 1.5 times V2. Now we have the correct numerical setup. We're all done. However, we should indicate units if we're doing a numerical setup. So 125 ml equals 1.5 atmospheres, and we just leave this at V2. Okay, and it's important to indicate units here because the grader doesn't know if you're talking about atmospheres, kilopascals, torrs, millimeters of mercury. You could be talking about liters, milliliters, all these different things. So that's why it's important to indicate units so that your grader knows you know your stuff. Okay, question number 10. This doesn't relate necessarily to gas laws, but it should be something that you should be familiar with from unit conversions. Everything in chemistry builds upon the previous unit to tie it into a bigger picture. So it's good to review how to do a unit conversion from milliliters to liters. Okay, so we have 125 milliliters for our initial volume. And now we're going to multiply that by 1.0 times 10 to the negative third. Now we get 0.125 liters. If you don't remember unit conversions, I tell my students to draw it out online. Although some may disagree with me, this is how I learned. King Henry's daughter, Ursula, died chasing monkeys. So this is kilo, hecta, deca, the unit that you're working with, deci, centi, and milli. So if we're going from milli to the unit, which is liters, we know there's a jump, 1, 2, 3. So the decimal place moves back 1, 2, 3. We see 1, 2, 3, and now we get our 0.125 liters. So if you want to do it that way, you can. If you want to plug it into a calculator using your conversion factors, completely up to you and how your brain works. Okay, let's look at another problem. The gas volume in the cylinder is 6.2 milliliters, and the pressure is 1.4 atmospheres. The piston is then pushed in until the gas volume is 3.1 milliliters when the temperature remains constant. All right, let me pull out my notes here. Okay, so it asks you to calculate the pressure in atmospheres after the change in volume, show all your work, and then from there, we're going to record our answers. This is asking for numerical setup and a bottom line for the answer. Okay, let's write out our formula. P1 V1 over T1 equals P2 V2 over T2. Okay, we hear that the temperature remains constant in this syringe. So let's cross out temperature. And now we get a final formula of P1 V1 equals P2 V2. All right, so now let's plug things in. Okay, so we have 1.4 atmospheres. All right, and our initial volume is 6.2 milliliters. All right, and we're calculating the second pressure, so we can keep that as P2. And our second volume is 3.1 milliliters. All right, and we just solved algebraically. And if you know how to solve algebra, should be pretty simple. 2.8 atmospheres. So our final answer. Now this makes sense because we're decreasing the volume here. So therefore our pressure should increase. Because don't forget, pressure and volume, inverse relationship. Okay, let's look at something different. So a sample of helium gas is in a closed system with a movable piston. The volume of the gas sample is changed when both the temperature and the pressure of the sample are increased. The table below shows the initial temperature, pressure, and volume of the gas sample, as well as the final temperature and pressure of the sample. So what is the question asking? It says, in the space below, show a correct numerical setup for calculating the final volume of the helium gas. Okay, so this isn't too bad. Let me just pull out my notes here. So I make sure I write the correct numbers. Okay, now temperatures indicated, changes, pressure is indicated, it changes. Our question is finding that final volume. So let's get our formula up. P1 V1 over T1 equals P2 V2 over T2. Okay, and it says correct numerical setup. That was a horrible line right there. Correct numerical setup. Okay, so let's plug everything in. So initial pressure, 2.0 atmospheres. Okay, and our initial volume is 500 milliliters. Okay. Our initial temperature, it's already in Kelvin, so we don't have to convert from Celsius to Kelvin. Our initial temperature is 200 degrees Kelvin. Don't forget, we're showing a numerical setup, so we do want to indicate units in our work. Our second pressure is 7.0 atm. Our second volume is what we're solving for. And what's our final temperature? We're going to get 300 degrees Kelvin. Okay, we have our numerical setup. And that's it for that question. Don't solve the math through if it just asks for correct numerical setup, too much room for error. However, if it did ask us to solve this, then we would simply cross multiply. Cross multiply and then solve for a variable, which is V2. Simple algebra. Okay. So, in a laboratory, a glass tube is filled with hydrogen gas at a very low pressure. When a scientist applies high voltage between the metal electrodes in the tube, light is emitted. The scientist analyzes the light with a spectroscope and observes 4 distinct spectral lines. The table below gives the color, frequency, and energy for each of the 4 spectral lines. The unit for frequency is Hertz, or Hz. Okay, doesn't really seem like a gas law problem or a problem using KMT. However, this particular question from the question series I picked out because the question is identify one condition not mentioned in the passage under which hydrogen gas behaves more like an ideal gas. Okay, so we know there's a difference between ideal gases and real gases. So real gases, how gases actually behave. But according to KMT, which I talked about in my previous video, ideal gases are what those apply to. So it's more of a theoretical thought process. So for a real gas to behave most like an ideal gas, we're going to need high temperature, get that high kinetic energy. We need low pressure. Reason being, low pressure, the gas particles have little to no attraction to each other. They have more room to go around. If we have a high temperature, well, then these have fully elastic collisions. Now we know this is not exactly ideal for a real gas because if I increase the temperature, I'm going to have an increased pressure and vice versa. Because we know the relationship between temperature and pressure is a direct relationship. However, this is when a real gas really acts like an ideal gas. So in the question, it indicated pressure. We're already at a very low pressure. So the question asks you to identify one condition that's not mentioned in the passage. So if we put, oh, let's decrease the pressure, you would get that wrong because we've already mentioned pressure. So therefore, we want high temperature. That's all you have to put. Increase temperature. Needs a higher temperature. Draw an arrow with temperature. Doesn't matter, just indicate that you want to increase the temperature. So if there's one takeaway from this, it's that real gases act most like ideal gases under high temperature and low pressure. They really like to ask this question on exams. Okay, let's move forward and solve a different problem. Now, the Regents exam loves to ask questions with pistons. The cylinder A has a movable piston, contains hydrogen gas. An identical cylinder, cylinder B, contains methane gas. The diagram below represents these cylinders and the conditions of pressure, volume, and temperature of the gas in each chamber. Okay, so if we look at the hydrogen gas, let's assume this is H2 in gas form. This is more of an FYI. Methane is CH4. Okay, so this has 5 atoms. This has 2 atoms. So we know the methane, is a larger molecule. Now let's look at the different variables, pressure, volume, temperature, and we notice they are exactly the same. So compare the total number of gas molecules in cylinder A, the total number of gas molecules in cylinder B. Well, do you remember Avogadro and his law? Same variables, especially same volume, same number of gas particles, even though hydrogen is much smaller. They got really small atoms, and there's only 2 atoms in hydrogen gas. Carbon is pretty much bigger than hydrogen, and we have a total of 5 atoms. However, despite their sizes, total number of gas molecules in cylinder A to B is exactly the same. So we can say equal number of gas molecules. This is, again, according to Avogadro's law. So Avogadro's law, in my opinion, is one of the easier ones. Okay, show a numerical setup for calculating the volume of the gas in cylinder B at STP. Okay, so right off the bat, we know we're going to have to use our combined gas law equation. These should be 2's, my apologies. Okay, so let's go back. 1.2 atmospheres, 1.25 liters, 293 Kelvin. We're calculating the volume, and we're looking at cylinder B, but it doesn't really matter because cylinder A, cylinder B have the same exact variables. Okay, so if we look at the pressure 1 is going to be 1.2 atmospheres. Our volume is going to be 1.25 liters. Initial temperature is 293 degrees Kelvin. Now, what's up with this problem? Because this problem doesn't indicate what changes there are in pressure and temperature. So I know I'm solving for V2, which I'm going to write here in a second, but what's the new pressure and what's the new temperature? Take a look. STP. I changed it to STP. Remember the beginning? I told you STP is standard temperature and pressure. So the temperature is going to equal 273 degrees Kelvin. if it's standard, and the pressure is going to equal 1.0 atmospheres. So now we do have our change in temperature and pressure. So pressure changes to 1.0 atmospheres. We're solving for V2. And now we have 273 degrees Kelvin. Asking for numerical setup, do not do the math full on out. Otherwise, it's too much room for error. If we would just cross multiply through, isolate a variable, we have our answer, just basic algebra. Question number 18, still applying to the same graphic. State a change in temperature and a change in pressure that will cause the gas in cylinder A to behave more like an ideal gas. This is something that you're going to have to memorize. We talked about this a couple slides previously. But if we want a real gas to behave most like an ideal gas, we need to increase the temperature, decrease the pressure. Under those conditions, our gas, in this case, our methane gas, is going to act most like an ideal gas. So memorize that. Higher temperature, lower pressure. Higher temperature, lower pressure. That's when a real gas behaves most like an ideal gas. If this was a multiple choice question, it would give you a few different options for a combination of pressure and temperature. And it'll say, under which conditions does the methane gas act more like an ideal gas? Well, you're going to look for the increase in temperature and you can look for the decrease in pressure. Once you memorize that, all the rest of the questions are going to be easy, referring to ideal gases. Okay, so that is it. Thank you for watching. Stay tuned for more videos in the future, and as always, happy studying.